What's good, y'all? Welcome back. You made it to the last video of the circuits mini lecture series. In this one, we're just going to do a little bit of intuition building and wrap up. We've only got about 5 minutes, so I'm going to make it pretty quick. Let's jump in. Okay, the first little example I wanted to talk about was a space heater. So my housemates and I recently had a discussion about the energy bill and who's responsible for what. There was some concern about the impact of a certain space heater on the overall bill. So a calculation we did recently was how much energy does a space heater really take? So a space heater takes up 1500 watts on max power. So max power of a space heater is 1500 watts. So what does that tell me? It tells me that every second a space heater on maximum power dissipates 1500 joules. So the question was, if I ran a space heater for 8 hours a day, how much energy would I use? So if I ran a space heater for 8 hours a day, how much energy would I use? So if I wanted to convert that to energy, energy is just power times time. And since watts are in units of joules per second, I can calculate the energy by multiplying the wattage by some number of seconds. So it'll be power times the number of hours in a day times the number of minutes in an hour times the number of seconds in a minute. Okay, so it'll be, the energy is going to be 1500 watts times 24 hours. I'm not doing 24 hours in a day. I'm saying how much energy is it if I run it for 8 hours a day. So the energy it takes in a day, 8 hours times 60 minutes per hour times 60 seconds per minute. And what do I get out? I get 1500 times 8 times 60 times 60. I get 432000000 joules. Okay, so to make this into a little bit more of a circuits example, here's what I want to do. Let's say that I know that I've attached my my circuit to the wall. And for simplicity's sake, let's just pretend that the wall is 120 volts of DC current. So this is my wall. And I will model my space heater as just some resistor. Okay, so I know that it dissipates 1500 watts. So I have two questions. The first question is, what is the size of this resistor? And the second question is, how much current is flowing through my system? So the simplest way to address this question, I think, is just to start with our basic definition of power. Power is change in voltage times current. So this resistor, the space heater, is the only thing standing in the way of this battery. So it's going to absorb all of that voltage. The power dissipated by my resistor is just going to be 120 volts times the current. So since I know the power is 1500 watts, I can just solve for the current. I is just 1500 divided by 120, which is 12.5 amps. Okay, what does that tell me about the resistance of my space heater? How big is my space heater's resistor? Well, I know that the change in voltage across a resistor is just negative I times R, where I is the current through that resistor and R is the resistance. So I know a couple of things. I know that the resistor absorbs all of the voltage from this battery. There's nothing else in the way of the battery's head and tail. So delta V resistor is just 120 volts. Negative, so I'll put a negative on there. I is 12.5 amps, so negative 12.5 amps times whatever R is, the resistance. So the resistance is just going to be 120 divided by 12.5, gives me 9.6 ohms. Okay. Lower resistances would correspond to higher currents, and as a result, higher power. Kind of weird. So if you have a higher wattage bulb, that actually corresponds to a lower resistance of the bulb. Okay, I'm going to go slightly over time here to talk about circuit reduction. Sorry, folks. So let's just real quick hit a more complicated circuit. So what I'll do is I just want to show a series of resistors like this. So I have a resistor up here, and another one up here, and then one down here. This is to kind of try to demonstrate the order of operations of circuit reduction. So first what I do is I look for, I'll label the resistors, resistor 1, resistor 2, resistor 3. To reduce this to our simplest circuit, to talk about how much current is coming out of our battery, let's say that this has some battery voltage E, I have to look at my circuit and decide which of the resistors can be combined. So, for example, I cannot combine resistor 1 and resistor 3 because resistor 1 and resistor 3 aren't connected perfectly in parallel. They don't have head attached to head. Or they do have tail attached to tail, but they don't have head attached to head. R2 is the one whose head is attached to R3's head. So the first thing I have to do is reduce R1 and R2. So my first reduction in my circuit would give me something like this. I would have a battery in its same place. I would have an upper resistor that is R1 plus R2 in terms of size. And then I have a lower resistor that is still R3. There we go. Okay, my final circuit reduction, now that this is two resistors in parallel, is to just, add them up together in parallel. So my final circuit will look like this. I'll have my battery in place. I'll have my resistor. Now we're down to a completely reduced circuit, a completely simplified circuit. So the equivalent resistance of my upper 3 resistors in the first picture is just going to be R equivalent equals 1 over R3 plus 1 over R1 plus R2. Now the reason I've included these together is because that's the resistance. The thing on the bottom, R1 plus R2, is the equivalent resistance of this upper half-reduced resistor. Okay, and then I invert that. So that tells me the equivalent resistance in the simplest possible circuit. Using this and knowing my battery voltage, I can figure out how much total current is being drawn from the battery without knowing that a priori. Okay, and we're a few minutes over time. What I want to leave you with is a quick little picture, a rough conceptual map from fluid to electrical circuits. And there was some talk last time that it was hard to see, so I'll make it a little bigger and bring it to the front. Okay, rough conceptual map from fluid to electrical circuits. And I'll cover myself up too. Okay. So pressure is like voltage, flow rate is like current, resistance is like resistance. The energy density equation is like Kirchhoff's voltage law, and continuity is like Kirchhoff's current/junction law. So if you're stuck on a problem and are having trouble figuring out where to start, this table can be a good way to carry over your intuition. All right, I think I will go ahead and leave it there. Thanks for tuning in for this round of lectures, and I'll see y'all next week at the latest.